Hello everyone, and thank you for registering for this live webinar. My name is Fidel Tujizimana from the University of Johannesburg, South Africa, and I will be hosting this webinar on behalf of the Early Career Member Network of the Metabolomics Society. This is our 11th of our webinar series, and it is brought to you by the EMN committee. Currently, the webinars are free for all to attend by the courtesy of the Metabolomics Society, and I would like to inform you that all material will be recorded and uploaded to the Metabolomics Society website, so you can have access to the live content at your own convenience. And Carl, the next slide. Please connect with the Metabolomics Society on Facebook, Twitter, LinkedIn, as shown on the screen. And you can share your ideas and suggestions at the email address on the screen. The next slide, Carl. Before introducing our speaker, I would like to introduce to you to the new Metabolomics Forum, which is a platform way to talk and discuss any subject related to metabolomics, be software, database, and if you have any question related to metabolomics, you can post it on the forum and get answers from other users who are experts in the field. Please visit the forum, create your own profile, and use this platform to talk and discuss metabolomics. The link is displayed on the screen. The next slide, Carl.
Yes, there you go.
Thank you. So today our expert speaker is Dr. Carl Brunius. Dr. Carl devotes the majority of his time to develop data analytical tools for data cleanup, validation of predictive multivariate modeling from batch statistical and machine learning origin, and joint analysis of multiple datasets such as multi-omics. He is currently employed as a senior researcher at Chalmers University of Technology and at the Swedish University of Agriculture Sciences. During the webinar presentation, you are welcome to post your questions using the questions option on your screen. And at the end of the presentation, I will present the questions to our presenter and he will answer them. I will pass to you, Carl, for your presentation. We look forward to learn from your presentation. Thank you.
Thank you so much for that. And thank you all the participants who are here. It's amazing to be able to give a presentation on this topic to so many interested people. So let me first say a few words about myself. Like Fidel, after his kind introduction, my background is actually in chemical engineering, and I've sort of switched over to data analysis. And what I do in my job is to build tools and methodologies for analysis of metabolomics data and also other omics data. And what we do is normally to design tools as solutions to our acute problems that we're facing in predominantly metabolomics and nutrition. So this work that I'm going to present today started out as sort of an in-house toolbox to solve particular problems that we were having to face, and then all of a sudden we had gathered quite a lot of really nice tools, and we realized that we sat on some pretty unique solutions and ideas about how to clean up data. So I'm really happy and excited to be able to share this with you today. All right. So what am I going to talk about? Well, it's going to be a little bit about the metabolomics workflow, just to put us on the same page in the beginning. And then I'm going to go into the two main aspects, which are going to be between batch alignment, which is not something which is regularly done in the Metabolomics Society. And when I do that, I'm also going to talk a few words about soft within batch signal intensity drift, which the community is much more well aware of, and we've got a slightly different take on that. And I'm going to wrap up with some conclusions and open up for questions. So please make sure that you write down your questions in the question thing of the webinar tool, so Fidel can go through them and fish out interesting questions, which I'm sure you'll have quite a lot of. And as I said, it started as an in-house toolbox, and I was very inexperienced as a coder in the beginning. So if you find this interesting and you're going to download some code, then some of the things are not going to be the most beautiful code, but it does the job, and that's the most important thing. All right. So just as I said, to put us on the same page, what are we talking about when we're talking metabolomics? Well, we tend to see it as metabolomics as the interaction between the gene cascade, the central dogma in biology, and the exposome. So the gene cascade is from the gene blueprint down to the actual construction, which is the phenotype, and the exposome is what we're exposed to along the way. This interaction is reflected as the phenotype, which we, of course, measure by metabolomics. And just a straightforward sort of workflow in like simplified form is going to look something like this. Like, we start with a research question. This is what we're interested in, and everything further downstream of that has to reflect our original research question. And I'll put down some sort of guiding questions, which are, yes?
Sorry, Carl, sorry to interrupt.
I've written down some sort of guiding questions about, in our line of work, what can such a research question be? Like, what are the metabolic effects of some kind of food exposure? Or will some kind of intervention result in a reduced risk of adverse health effects of something? And the experimental design, of course, needs to be adapted to this research question. And very often we are facing controlled interventions or observational studies with association studies, these kind of things. And that spills over in the data collection. And we need to be aware, of course, that our choice of measurement technique, for example, NMR versus LCMS or GCMS or capillary electrophoresis MS, whatever, and that's going to impose some limitations on what it is we can actually measure. For example, NMR is very robust, but you sort of can measure highly abundant endogenous metabolites, whereas if you want to find minor constituents in a dietary exposure pattern, then LCM is going to be a better choice. But of course, not only will it influence what you can see, but it will also impose a certain error structure on your data, as well as the sampling. If you're going to take blood plasma samples, do you standardize the time from the needle to the freezer, or do you have variability, which will affect some kind of biological variability that is not related to your research question? Then, of course, we go into data analysis and in conclusion, and everything really needs to be reflecting this research question that we're talking about. But how can we help the data analysis when we do the data collection? That's what we're going to look at here. So in between the instrumentation and the data analysis, we're going to be sitting with a bunch of raw data, which is fantastic. But what do we do now? So general workflow in an LCMS metabolomics experiment is when you're sitting there with your raw data, you do some peak picking, peak alignment, normalization. Those are the three fundamental operations that we're going to do. And there are several options for all of these. For example, if we're looking at peak picking, there's all the way from sort of easy version, like use the vendor software and automated settings. But anyone who's gone into serious peak picking knows that your parameter settings will greatly influence the data, the peak table, the quality of the data that you're going to be sitting with in your analysis later on. So we're actually using another approach. We're using XCMS through R, and we do a careful investigation of peak picking parameters. And what we found during multiple batch experiments is that alignment is somewhat of a problem, because we tend to mix or combine variability from within batch effects time differences within a batch are going to be relatively small. But between batches, you're going to clean your column, which means that when you shift from one batch to another batch, then you're going to see very large systematic differences. So we need some kind of approach to take that into consideration, and which is something that we developed. Normalization also should be separated within batch and between batch normalization. But in this area, there's more. We're more mature as a community, I would say. But we were happy to collect our experience from cleaning up data in our in-house pipeline and tools into an R package, which is called Batch Core. As I said, we realized that we had some approaches that we thought were pretty unique, and we wrote a paper to tell the world about it, and we got some really positive feedback from editor and reviewer, and also had the opportunity to present this as a poster at the Metabolomics conference in Dublin, where I may have spoken to a lot of you people, because I've spoken about this, and there's an enormous interest in the community about how to deal with these issues. So, yeah, let's go into the real work now. So what's the problem of systematic misalignment? Well, in this slide, I tried to visualize that we got a 3-batch experiment, and we're going to look in the retention time domain at 2 true peaks, two true metabolite features, if you will, and then we're going to call them peak A and peak B. What you're normally going to find is that the variability in retention time per batch is going to be relatively small, like I just said, and this is exemplified by the blue, green, and red features that you're going to find that if we just optimize using, for example, the IPO package or your knowledge of chromatography, then you're going to run the risk of actually dividing your true peak A into 3 distinct features, A1, A2, and A3, which are going to be batch specific. And you're going to do the same thing for the peak B. So instead of having 2 features, you're going to have 6 different features that are going to be beautifully separated between the batches. And if we are faced with this situation, we got 3 main options. One option would be to do the forced filling, which is in XCMS called fill peaks, which is a hard integration between consensus borders. So then we're going to basically tell the machine to find out what is the integral at these different features. But since we have systematic misalignment, it will fill in a bunch of zeros, which is not relevant. So we're going to find that we split our relevant information A and B into non-relevant information A1 through A1 all the way through to B3. We got a different choice, which is imputation, which a lot of guys are using, and we're using that as well, but not for all purposes. So then we're going to try to find out, well, considering that we have missing values, what would probably be the true values? So then we're going to use some kind of K nearest neighbor or random forest imputation or something like that to find out estimated parameter values. So then we're going to actually impose noise in our data structure. It's probably going to be a better choice than fill peaks if you have systematic misalignment. But we think that probably we should do some kind of alignment of these peaks, and the naive choice would be just to increase the bandwidth setting of the peak picking. And then we would force A1, A2, and A3 to be picked within the same peak A. So that would do the job. But that also runs the risk of aligning in features that actually don't belong in there. If we got a peak C, which is very close to peak A, then we would find that peak C would be introduced into peak A, and that would contribute to noise in our data. So we devised a different algorithm for that instead. And it looks a little something like this, and this can be slightly intimidating, but let's try to go through it semi-slowly and see where we end up. Okay, so in the red thing in the beginning, we got our index. That's going to be our multiple batch feature matrix. And then the trick here is to look at features not on the individual sample level, but on the batch level. So we optimize the peak picking for each feature, which can be batch specific. So we artificially split some of the features. And then we're going to look at, well, what is the consensus within the batch? Is the feature there or is it not there? And on the right-hand figure, you're going to see 5 different features in a window with a retention time on the x-axis and M over Z on the y-axis. And we're going to look at, they're called different things. It's feature 5007, 8, 9, 10, 11. Those are the feature names. And then below that, you're going to see 3 numbers, and those are the batch flags. So we say that if this feature is absent from more than 80% of samples in the batch, we say that it's absent from the batch. And if it's not absent, it is present. And then we flag that as if you're going to look at, for example, 5010, it's got a 001. It's missing from the first batch. It's missing from the second batch, but it's present in the third batch. So that gives us the information on batch level, if the feature is there or if it's not there. Then we're going to say, we're going to impose 2 criteria to find if it's a candidate for alignment. So basically what we're going to look at is to find if these features are close to each other. That is, if they are close in retention time and if they are close in M over Z. And then one can ask, what is sufficiently close? Well, M over Z is easy. We get the instrument resolution, for example, 2 ppm. And then we're just going to impose that as our criterion. Retention time, we get that from XCMS, for example. Between batch time adjustment, it's going to be 15 seconds at maximum. So that will give us the window within which they can be considered alignment candidates. And then we're going to see, well, can these features actually be combined? For example, if you see 5008 and 5010, they are both present in batch C, in the third batch. That means we cannot combine them. But 5007 and 5010, they are what I call orthogonally present. So then we can combine them. But you're also going to see that in this instance of these 5 features, 4 of them can actually be combined together, 7, 9, 10, 11. So then we need to disentangle these sort of multiple candidates. And once we sort out those conflicts, we're golden. And then we combine the features that should be combined. And that leads to a situation in which we can actually optimize peak picking parameters to find the narrowest bandwidth setting so we can really trust the peaks, and then we fix the problem of misalignment afterwards. And you will see some result data on that, why this is good. So I'm just going to go into some of the computer issues and how to work with this. So I do this in R because R is open source. My background is actually from MATLAB, but I tend to like open source solutions better. So what you need to do is to install R, and I would also recommend anyone working in R to install RStudio because that's a convenient environment. But since I'm not a hardcore programmer, I'm not up to the standard of writing official packages. So I maintain this in a Git repository called GitLab. So that's why you're going to need a tool called DevTools in order to install from Git repositories. And then it's maintained at this web address, gitlab.com/Brunius/batchcore. And to be honest, to install from Git is rather easy. Slightly more difficult in Windows because you need to install a few tools in order to do that. But Google is your friend. And there are quite a lot of code instructions on how to do that. If you're going to do some more serious package development, it's almost equally tricky between operating systems to get it up and running. But once you're up and running, it should not be a problem. All right. So if you're going to go into the repository, it's going to look something like this. This contains all the files that you need for installation and also some installation instructions. So you install the package from our command line using the dev tools, and it should be just working. Also, in your library folder, you will have the workflow example folder installed, in which there is a fully working script using our data that we used for the publication of this paper. So you should be able to reproduce everything, and it should just work straight out of the box. Installation is fairly straightforward. In the bottom left corner, you're going to see the DevTools install command, and it's just going to install the package and some dependencies. And as I said, you're going to find in the library, which depending on your operating system is going to be found in some different locations. Then you're going to find this script file. That's sorry. And how to do this coding. It looks like there's a few lines of code to do this between batch alignment, but most of this is actually cosmetics to bring out feature metadata, like what is the MZ and the RT of the features. But the three important stages there are the batch flag, which is the algorithm to just flag per batch which features are present and absent. Align index to find out which are the features that should be aligned. And then there's the batch align function, which actually performs the alignment in itself. And this is a very quick procedure. In a data set of 90 observations and something like 11,000 variables, we're looking at a total runtime of 14 seconds on a MacBook Pro. On my old PC, it took something like 25 seconds. So that's not going to slow you down, really. It takes much more time to get the data into the proper file format than to do the actual calculations. And these are the results that are going to be interesting to look at. So you're going to see this figure, and it's got the red dots for XCMS peak picking, depending on your bandwidth setting. What is the window that you allow for peaks in retention time, right? So just by looking at the XCMS raw data, we would expect, if we don't do this between batch alignment, that 15-second interval is needed to make sure that all the same peaks are found as the same feature. And then we're going to get something like 9,800 features. And if we decrease this bandwidth setting, we're going to find that features are going to jump out of the old features. So you're going to pick more and more features. But the problem is, when we're going to find more and more features, is that we don't know if we're actually going to disentangle true features or if we're going to artificially split true features between batches. So the lower bandwidth leads to more features, but we have no way of knowing which ones are true and which are artificial splits. So that's why we're going to do this batch align to recombine the artificial splits. And what we're going to find, and I get this to work properly, is that we're going to have these together are the total gain in peaks, going from 9,800 up to 11,800. So it's a gain of 2,000 peaks. However, not all of those are true peaks. Some are actually artificial split, and that's going to be 500 that are artificially split and about 1,500 that are going to be true peaks. And now we're going to see that it's actually a dual benefit of doing this. By decreasing the bandwidth setting, we're increasing by roughly 15%. We get 15% more peaks. But probably even more important, those 15% more peaks were previously hidden as noise in the 9,800 features that we originally had. So we're cleaning up data and introducing new data. So it's a dual benefit, and this has really, really helped us in our analysis to get higher quality data. So I hope that convinced you that this is a good thing. So let's now look at, let's switch focus to signal intensity drift correction. Just to put a slight overview of this area, so the first question that we're going to face is, should we correct for variability? Because we know that in an MS system, the instrumental response is not going to be constant over time due to build-up in the interface. There's going to be other factors governing this, impurities, etc. So in some labs, they actually don't correct for variability. They just apply some kind of quality cutoff. And one of those cutoffs could be, for example, what is the coefficient of variation in the QC samples? If that is below 30% or some other figure, then we say we keep the feature. If, however, this, why did we choose 20 or 30%? And then there are some other more pragmatist guys that are going to say, well, if the coefficient of variation of the biological samples is larger than the QC variation, then we get something interesting. This is a pragmatic approach, which is, I would say, it's very logical and very nice. But still, we think that we can improve the quality of the data by modeling the drift over time and then back calculating away this drift. So if we instead say, yes, we want to correct for the variability, then we have a choice. Should we use QCs for doing that? And I guess you're all aware of the famous Dan paper in the Nature Protocols from 2011, I think, that they're using QCs for multi-batch experiments, and it's a really nice piece of work. But in the last years, we've also seen really nice work on population normalization. However, at this point, we say we want to go with QCs because we believe them to be sort of fairly true. They have got very low variability. But anyway, regardless of your choice, the following question is, should you allow for variability in the instrumental drift? And then the general assumption was for a very long time that no, the general intensity is going to be the same. The change is going to be in general intensity. Like if the sensitivity goes down for one feature, it's going to go down for all the features. However, we know this to simply not be true because we got competing mechanisms. And on the other hand, we got the other extremes, for example, the Dunn paper, and they're going to do some full variability. So you model the drift per feature. And that has led to some problems in that we're overfitting to instrumental variability within each feature. So what we say instead is to let there be some variability. And then we put that into our package, and I'm going to show you this right now, actually. And again, it looks slightly daunting, but please let me go through this and you'll see it's not that complicated. When I say some variability, what we're going to do is we're going to take our batch data, we're going to scale our variables so they are comparable. So you're going to see 4 bar graphs here. On the upper part of each, it's raw data. We're going to cluster the guys that have the same sort of similar drift, and I don't have time to go into the details of this clustering algorithm right now, but it's a nice piece of work, I would say. And we find that all of these guys share the same sort of general, I forgot to put the pen on. All of these guys share the same sort of general variability pattern, but you're also going to find that there's a lot of instrumental variability in each feature. So if we fit per feature, then we're going to model noise. By using this approach, we're going to pool a lot of data so we find one smoothing curve for each cluster. feature. And we're going to find that even with something like, we normally pick something like between 10 and 30,000 features in a metabolomics experiment, that we're going to find that there are about 25-ish clusters, 25 different drift patterns, if you will. And then we model them per pattern instead, find out the drift function, we apply that to the data, and we end up with a normalized or signal intensity drift corrected data. And we do that for each cluster. This is one cluster, and there are 4 clusters here, as you see. You're also going to see that on the top of each of these 4 clusters, that they have very unsimilar behaviors. In the top left corner, you see that there's pretty much no drift there at all. And in the bottom left, you're going to see its signal intensity is decreasing. So sensitivity is decreasing, and then there are different patterns on the right side. So we think that this is a pretty good way to find a compromise between allowing for multiple drift patterns, but not overfitting to random noise within each specific variable. So the code to do this is fairly straightforward. There's some lines to convert your data into a friendly format which the real algorithm can read. So that's where the real work is being done. We correct for the signal intensity. We can make some plots using report equal true, and then we can look at all the data. What does it do? What does it look like? And we can also accommodate different reference sample strategies. And unfortunately, I don't have time to go into that, but we are normally employing 2 different sets of QC samples. One is for drift correction, and the other one is to assess whether or not we should do this drift correction. Because, I mean, if they're not within this process of drift correction, and if they improve the data of reference samples, then we do the drift correction. But let's talk about that some other time, or read the paper. And we're going to see that we get some pretty good correction of data. So I'm going to leave the last few minutes just to say other things that we're doing. So warning, there's some shameless self-promotion ahead right now. So if we're going to look at some of the projects that we're doing are related to, for example, biobank samples, because we're doing nutritional epidemiology, for example, and then we're going to work with biobanks. And then the question is, can we use these samples if we don't do the sampling ourselves? Because we know that they're going to have variability, for example, in sampling procedure. And then we can, yes. So from drawing a blood sample, we're going to centrifuge this, and then we're going to do our experiment. However, this part of the workflow is very often non-standardized and introduces biological variability that we simply don't want. But then our idea, what we're doing, is to find metabolomics data that is relevant to predict what goes on in the sample, and then we use that to clean up the data. And as it were, the algorithm for doing that is almost exactly the same as the batch core signal intensity drift correction. So when you do different types of analysis, you can reuse ideas and you can reuse code so you work efficiently. And what do we use that for? Well, of course, there's, like always in metabolomics, we want to find something in relation to research question. In our case, we're very much interested in exposure to whole grain rye, for example, and then we can recruit people and have biospecimen and make some kind of predictive model using some kind of big data modeling. And the workhorse, of course, in metabolomics is PLS, but we're also using support vector machines, artificial neural networks, random forest kind of things, but also trying to incorporate different types of modeling. So we base it on previous works by Westerhaus and colleagues in Amsterdam and Fieldsmotor and those guys. But we also incorporate variable selection within this, so we improve prediction performance and information density. It's not what this is about, but my point here is that we do this always in our friend R. So it becomes open source. And unfortunately, if you're going to use a program like Synca or Scrambler, they're good for what they do. But if you want to customize workflows and make specific validation procedures, then you simply cannot do those things there. So we can also concentrate on making this easy to use in R, so no one is distracted from doing their real work of trying to put some biological meaning into this. And we can get some pretty decent predictions out of this. We recently got some money to go into joint analysis of multiple data sets because there are different metabolic subtypes, and how can we do that using different types of data analysis? So we have huge interest in these areas, not only in data cleanup. So just to wrap this up really briefly, so we do the data cleanup, we get improved data quality, and that's going to help us enormously in our modeling, our data analysis, to get more accurate results, which are going to reflect our research question better. We strongly feel that open source is the way to go, because one of the things that we have discovered is that we need control over our data pipeline, and we cannot get that kind of control using vendor software. That is our experience anyway. And also there's, of course, the aspect of collective learning, that if we do some kind of nice algorithm, someone else is going to take that, use that idea and work with it further, and then that's going to come back into the community, and development of really good algorithms is going to be better and faster. And in the future, we're going to go into regarding data correction. We have ideas about integrating our ideas about multiple drift patterns with non-QC normalization. I mean, using the sample population itself for normalization, which is highly relevant in the cases where your QCs are not representative of your sample population. And then, of course, we're currently pursuing several tracks in multivariate modeling. Not least, we're looking at joint analysis of multiple data sets, or multiple data domains, I should say. So by that, I thank you very much for listening to me for about 40-ish minutes. I want to thank all the collaborators that we have, my boss, Rickard Landberg, and our small group doing metabolomics, and all our collaborators on the experimental side, instrumentation side, and data analysis. We got some really, really nice people in Europe doing data analysis, and everyone's really friendly and open for collaborations. And so thank you so much. And now I leave to Fidel.
Thank you. Carl, can you hear me?
Yes.
Yes. Thank you so much for your wonderful presentation, and apologies to those who couldn't hear him very well. The webinar is recorded, and they will see if they can do any cleanup and post the webinar on the Metabolomics Society website, and you can go back and listen to it at your own convenience. Before we go to the question session, just to say that this is the last webinar for this year. There are more webinars to come next year from January. Please stay tuned, and they will be advertised, and you can, and I'm sure they will be more interesting to come. For questions, Carl, I have a few questions for you that were posted. One question reads, so if the 15% increased peaks the quota is still noise, or how do you judge that?
I didn't understand the question. The what is still noise? Sorry.
The quota of that 15% is still noise, or
no. There's no such thing to say that data is necessarily noise. It's true peaks, but if you have two peaks that are originally superimposed on each other, then those two together will form one noisy variable. But when you take that one out from the first superpositioning, you will have two different peaks which may contain relevant biological information. But that biological information was not accessible to you previously because they were superimposed and therefore noisy. So it's true peaks that we're extracting, and we get the dual benefit of having more peaks and reduced noise.
Reduced noise. Okay. Thank you. And another question. If you use the data as for correction, don't you risk removing the interesting rarity variance? Can you automatically determine the smoothing, or is this user defined?
But we need to remember that this function for correction that we're doing, let me see if I can go back to that. It doesn't want to help me right now. Let me see if I can find the slide briefly.
Okay.
We're almost there. Sorry, here. That these functions, they are based on the QC.
I can't see your screen.
You cannot see my screen. Let me try that again. Share my... This program is not treating me like a friend, I'm sorry to say. So it's giving me a lot of errors.
Okay, it's fine.
Sorry. Anyway, so from the picture I showed you previously, where we had 4 different clusters, they had 4 different drift patterns. Those drift patterns are not the sample population. So we're not removing biological information. We're actually modeling the sensitivity by looking exclusively at the QC samples. And what we know about the QC samples is that they should contain 0 variability. They should be flat along the injection sequence. They should have the same value each and every time they are injected. So if they are not flat, we take this curvature and then we back calculate to as if it was flat. And then we use that correction and apply it to our other data to make the quality higher.
Okay. Another question. Could potentially unique fragments be used to deconvolute closed peaks? Yes,
potentially, but we need then to remember that the specific fragments or isotopes or ANDAX, whatever we're going to see, they are going to come from the same molecular entity, that it's going to have the same retention time. So in the peak picking, they will have the same fragmentation between batches as we see for the mother ion or whatever it is we're looking at predominantly. So what we're actually going to find is that very often it's really a lot of features that are going to have the same artificial split between batches, and then we realize that they are isotopes and ADAX, and they will not help each other because the chromatography is identical between these.
Okay. Another, I think it's like technical questions. I read it as this. We have aligned data in a CSV file, rows and columns. How can one prepare the data to use batch normalizer? And what is the format to use?
So this is a very detailed technical question, which is fantastic. I would recommend you to start by installing the batch core package, and then look at the example data that is there. And it is there just for the purpose that you should look at that data, and then you import your data so it has the same structure. Okay. And if that is going to be problematic for you, then I suggest you drop me an email, and then we will find some time and you will upload the file on Dropbox or something, and I will help you.
Okay. Jessica, another question also sounds similar technical type. The batch core code, is it working after data mining with XCMS, or is it using its own data mining code?
Then I need to ask more to be able to, what do we mean by data mining? That I would say that XCMS doesn't do data mining. XCMS does peak picking. And by applying the batch alignment, I can have better parameters for XCMS. So I really go back to the peak picking in XCMS and do that again to find out, to get good settings. Or I can use my knowledge of the machine and of the chromatography and do it in a on-off.
Okay.
But because of this term data mining, I don't know, because this is not a method for data mining.
Thanks, Carl. Another question: how many QCs per sample would you say is needed? Would you recommend?
I think we have worked from QCs every 8 sample up to every 15th sample. And I would say normally, if you have good expertise in LCMS and you are working with this regularly and your sample preparation is good, then every 12 injections is good. I don't see that it's needed to do more than that. But if you are slightly less skilled, I would have it at every 8 injections or something like that.
Okay. Okay. There was another question here. Is the program easy to use if one is not expert in R?
Unfortunately not. No.
Yeah, okay.
If you get help from someone to set this up for you, so you get the script and then you can just repeat this from one experiment to the next, then it's easy to use. But your first times of doing this, you will probably need to do it together with someone who knows their way around R, because every time you start with a new package or a new function, there are always tweaks and little things. So it always takes a little time to get used to it.
Okay. Carl, thank you so much. I think those are the questions that were posted. And thank you for the answers. I'm sure those who still have questions, you got the email for Carl. You can still drop him an email, questions, and I'm sure he will be happy to assist where possible.
I would be happy to assist anyone with any questions on this. It's my job and it's my passion to do these things. So please feel free.
Okay. Yes. Thank you so much, Carl. And please stay tuned for our webinars from January. Thank you so much for attending.